Hey everyone, James here from JC Sharp. Thanks for joining me today. We're going to be covering off Liskov Substitution Principle. So first of all, before you go ahead and watch this video, again I would recommend that you watch the solid overview I did a number of weeks back. You'll find a link to that in the description of this video. There is also going to be some references back to open-close principle partway through. So if you're not already familiar with the open-close principle, again I'd recommend that you go and have a look at one of the videos I did for that. Again, there'll be a link to that in the description. And as with all of these videos that I'm doing for the solid principles, if you want to code along, there is also a link in the description to the GitHub repo that I'm using right at the start of this. So a quick recap on Liskov Substitution Principle then. So essentially what LSP is, and we'll refer to it as LSP for the remainder of this video, is that child class objects should be able to replace parent class objects without compromising application integrity. And what this essentially means is that those child class objects should just behave in exactly the same way that a parent class is expecting it to behave. And when they don't, and they behave differently, that's what breaks LSP. And that's what we're going to demonstrate today. So in front of us we have some code, and this code uses ducks to demonstrate LSP because ducks are awesome. We have first of all this public class of duck controls, and this is just responsible for taking a duck and making the duck swim and making the duck quack. Really straightforward, really simple. So as part of that we have our abstract class of duck with a swim and a make noise method. And then this is inherited by our real duck class, which for swim just returns true, and for make noise returns quack. And it's also inherited by our toy duck class. Now you'll notice some differences in here. As part of the swim, we check if it's turned on, and as part of the make noise, we also check if it's turned on, because as we know, toy ducks can't do anything unless they're turned on. Alongside all of this code, what I do have is a series of tests that help us check the scenarios as we go along. So we've got tests for the real duck, for swimming and quacking, and for the toy duck, for swimming and quacking. And if we run those tests at the moment, in the state the code's currently in, what we'll see is that the tests for the real duck pass and the tests for the toy duck fail. I think I did run them. I'm going to run them again because I missed it at the corner of my eye. So let's have a look at this toy duck can swim then. So at the moment, we're expecting it to return true, that the toy duck is swimming, but it's not. Why is that? Okay, so let's have a look at the toy duck class then. So you remember we covered very briefly a couple of minutes ago that we check if the toy duck is turned on. Now for the most part, this is always false. So if the toy duck is turned on, then we can swim, otherwise we can't swim. So how do we go about fixing this then? Well, the first thing we can do as part of the duck controls is we can typecast and we can check it that way. So let's go ahead and fix it that way. We'll run the test and you'll see that it works, and then we'll explain why that's not really a very good idea to do. So if the duck is a toy duck, and we'll put that in a variable for toy duck, then we take the toy duck and we turn him on. So this method at the moment within the toy duck class doesn't exist. So using Rider's shortcuts, we'll go ahead and we'll create that method. And in here, we will just go turned on equals true. So the first reason why this is bad is because we're changing the behavior of the toy duck. And what that means is that it's still not really behaving as the parent class is expecting. The fact that we've had to add this extra method in there that isn't part of the inheritance of the base class or anything like that isn't necessarily a bad thing, but it's also not the best practice to be doing. And what that means as well alongside that is that anywhere where we're checking and doing anything with a base class of duck, we'll have to do this typecasting, we'll have to do this checking because the toy duck behaves differently. So if we run this test now, what you'll see is that this passes because we're checking that it's a toy duck and we're turning it on. But you'll notice that the techno quack for the toy duck still fails. And this is because this code doesn't exist. And this is where we breach open close principle, because what we're having to do is use that code absolutely everywhere because we've introduced this toy duck type. And that's really not a good idea either. What we don't want to be doing is having to constantly modify methods or classes and their behavior just to compensate for a new type. So just to prove that it does work, if we pop that typecasting in here as well, we can also then run that method and the toy duck quacks will also work. But okay, that breaks OCP, open close principle, okay, and that's not great. So how do we really fix this? Well, the example that we're going to use probably in the real world isn't necessarily the best example, and we'll talk about why that is shortly. But for the most part at the moment, what we're going to do is we're going to do something very dangerous and make the toy duck self-aware. So let's remove these typecasting bits of code, and we'll go down to the toy duck and we'll remove that public method. And what we'll say, if is turned on equals false, then we're going to turn the duck on, basically. And then at that point, we know that we can just return is turned on. So essentially what we're saying is the toy duck is now self-aware. He knows he's turned off, so he's going to turn himself on and then he'll start swimming. So at that point, we can just return true, essentially. And we'll do the same for here. So if turned on equals false, then we will is turned on equals true, and then we can just purely at this stage return techno quack. And again, if we run these tests now, you'll see that they work. And that's absolutely fine. What we've done now is basically say that the toy duck works exactly as the parent class is expecting it to behave. And that's okay. In the real world, having this is turned on functionality within itself and turning itself on with the extra complexity of real world multiple inheritance from parent classes, you might find that ultimately this might cause some problems. But in our example that we've got here, it's probably better that we have whatever minor issues might be caused from this than the major problem of essentially not having the duck turned on. And for most intents and purposes, it solves the problem of LSP in our very, very simple, straightforward example. But as I say, in a real world with complex inheritance and multiple child classes inheriting from a single parent, you could find that even doing that is not necessarily a great idea. But as I say, for our stuff, it works okay. So there we go. That's a very quick rundown of Liskov Substitution Principle. Feel free to, after this video, to go ahead and try extending the duck controls. Maybe make yourself an extra method to make the duck fly. You could also perhaps look at introducing some different duck classes. Make some up as you feel free. And, if you've liked this video and you've gained something from it, please don't forget to hit the like and subscribe and ring for the notifications as well, because I am now a bit more back on the ball and there will be more regular content. So thank you very much for watching. I hope you've enjoyed it, and until next time, see you then. Bye-bye.